Very sorry about that. I will start from, I noticed that I was on mute. I will start from the beginning. All right. This is what I was saying. Mathematical induction happens in three steps. I'm sure you can hear me right now. Also, you guys should like the feeds if you have not given a thumbs up. Now, but what I was saying was mathematical induction happens in three steps. You should be very open-minded on this topic. It's quite very simple, very, very simple. You don't have to get to feel it's complex. It's very simple, very understandable. It's so simple that we only use three steps and we're done with the whole concept of mathematical induction. Three steps, and you must not skip anyone. So pay attention to what I want to say now. The very first step is the base step. This base step is more like a place where you can easily relate. That's the base step. And that's why you have to do it. Because for whatever you have been given, you have to start from a place where you can relate. That's the base step. Now, after we have made the base step, and the base step gives us a positive result, then we go on to make an hypothesis. And that's why we call the next step the inductive hypothesis. An hypothesis is a claim or an assumption about something. So we go on to assume that something is true. Now, after we're done with the base step, we're done with the hypothesis step, then the final step is the step where you then make a final conclusion, where you prove that that exact expression is actually true. So how do you do that? Look at this line here. Let me try and explain to you the whole concept of how you should view mathematical induction. So this is a place. This is a point. And this is a point. You first of all want to be sure that at this point where you are, let's say you are here, you want to be sure that this works very well, that this place you are works well. So you say, okay, I'm going to put a trial here. You put your feet here. Oh, you see this works. Okay, let's take this particular point as one. You put your feet here. You say this works. You put your feet to this point. Oh, you say this works also too. In some cases, you go on to probably put on 3. And after you're done putting on 1, 2, 3, you already feel more confident, and I'm sure that this is working. This is working. This is working. This is making sense. So you know what you do? You go on to do. Then you go on to say, okay, if I've walked this step, I stepped on this place, it worked. I stepped on this place, it worked. I stepped here, it worked. Now, I can assume that if I keep on stepping, if I step till K, I'm sure that it will work also. Because you're already sure that when you stepped on 1, you stepped on 2, you stepped on 3, it worked. So you will assume that if I keep stepping up until K, it's going to work. Now, so you go on to assume that at K, it's going to work. So these 3 things I put here is what we call the base step. The base step. What you can relate to, what you can make you can easily make a conclusion on, easily on the basis of what you know. Now, after you're done with this one, then you go on to assume. Now, you have not gotten to KO, but you just assume. That's the assumption step, what we call the hypothesis step. And after you're done with this assumption, the final step where you want to now finalize that, say, I'm sure that if I keep on stepping, I'm still going to be okay. If I've stepped on 1, I've stepped on 2, I've stepped on 3. If I step to K, I'm sure it's going to be okay. But before you then leave this place and confirm that this works very well, you need to now go on to say, after K, that will be K plus 1, is going to still be okay. That's the proof step. So that's just a diagrammatical way of understanding mathematical induction. It's all about starting at a point, making an assumption, then proving that after that assumption, the next thing after that assumption is also going to be true. That's all. So let's see an example very quickly. Once you understood what I've said, let's take an example. And you'll see how we're going to use just this step we have. You will see the base step, you will see the assumption step, the hypothesis step, and then you go on to see the proving step. I'm sure you guys can follow what I'm saying. Does it make sense? Now, look at something. Look at something right here. Now, I told you, don't forget we talked about 3 different steps. So look at how we're going to apply those things. That simple analogy I just gave you. 3 different steps, and then you're done with mathematical induction. Step 1. More like, let me see if I can draw my something here. Maybe we should draw something like that step here. Step 1 is on 1, 2, maybe 3. Then we go on, we say k, and we go on to say k plus 1. Let's see how we're going to use this step to answer these questions. The very first step now, look at what they told us. They told us that when you were doing 3 plus 7 plus 11 plus, when you kept on adding, they said this thing was going to be giving you n into 2n plus 1. That was what they said. That if you added 3 and added 3 and added 7, whatever answer you got, that means that would have been 10, right? 3 plus 7 is 10. That will be 2. Of course, that's n being 2 because you have added 2 of them. This was the 4. You adding just this one would be n equals to 1. If you added this plus this, that means your n was 2. They are now saying if you put that n equals to 2 into this particular place, the values you got here, the sum here, will be the answer here, that it works. That was what they said. So what do we do next? We first of all start, we don't argue that it's true or not. We go on to first try our base step. That means more like, as I explained in the analogy, act like you're moving step by step. Now you move from n equals to 1. Let's see if n equals to 1 actually even works. At least we can relate to that. We have data to relate with that. So what do we do? Fixing n equals to 1. We already know that our n equals to 1 now was 3. Of course, 3 was the very first thing we are adding there. We can see 3 there. So let's go and now check if this particular one is going to work. Let's see if what they said was working is going to work. So put 1 here because n was 1, and n being 1, we got our sum. We got our sum when it was 1 to be 3. So let's put for n being 1. That will be 1 into bracket 2, 1 plus 1. Please understand the whole concept and the philosophy around this thing. It's more like you move with your base, assume your k, prove for your k plus 1, and you're done. Now, if you're done with this one, what do you get? You get 1 times, this is 1 times 2 plus 1. That's 1 times 3. That's 3. Okay, it looks like it works. For the first one, all right, that's our first step. Take it at this point now that you have stepped on the very first staircase or whatever you want to see. You have stepped on this place. You see it works. It's okay. All right, we don't want to stop there. We want to make a new test. Let's test for when n was 2. That means when you're adding the first 2. You're adding the first 2 now. That means n was 2. When you added the first 2, from what you have here, this is 3 plus 7. That's 10. All right, 3 plus 7 is 10, bar. Good. Now, let's go on to now use the formula that they told us. That is it going to be true? So let's see. We have n into 2n plus 1. That will be 2 into 2 plus 1. This is 2 into bracket 4 plus 1. That's 2 into bracket 5. That was 10. Oh, nice. It's looking right. It's looking right. This is me on my second step now. I've stepped on the first one, it works. I've stepped on the second base step, it works. Let me try and see, maybe I can, let me decide to step on the third one. Now, that's n equals to 3. So what do I do next? I check my n equals to 3 from my normal data. I see 3 plus 7 plus 11. That's 21 from my normal data that I can see. You know, that's what the base step means. Base step means something you can relate to. Don't forget, when I was giving you the analogy, I drew your picture here. This is where you are. So you can easily relate to what is here. So related to 1, you said it works. Related to 2, sometimes it's possible that it's only 1 and 2 you'll be relating with. You may not have enough data for doing the third one. It's still okay. Even some cases, even some people will argue that doing just testing the first one is okay. But just for the sake of real explanation, let's decide to test the third one. So when n was 3, that means we are adding the first 3. We added 3 plus 7 plus 11. We got the sum there to be 21. When we added the sum of the first 3, we got 21. So let's now go on and confirm from that formula they gave us. Is it going to be the case? So that will be 3 into bracket 2 into bracket 3 plus 1. That will be 3 into bracket 6 plus 1. That will be 3 into bracket 7. That gave me 21. Wow. So it also works. So from what you can see right now, you can see that the 3 base steps works perfectly. Now, you see, don't forget when I was explaining with the analogy, I said, at this point, you can now go on to make a conclusion that if you have worked on the first step, it works. Second step, it works. Third step, it works. You can assume that, okay, if I kept on working, I worked on the 4th, the 2nd, the 5th, the 6th. If I worked on the kth one, it's still going to work. Since I've tested for 1, 2, 3, it's going to still work for the k. That's where, so all these 3 things we have done here, all these 3 things is your base step. We just use this one to what we can relate to. These are what we can relate to. The next step now is what we call the inductive hypothesis. I told you hypothesis, the word hypothesis means assumption. It means when you are making a claim or an assumption. So since we have stepped on the first step, we have stepped on the second step, we saw this work, these 3 base steps works. We can go on to now assume. We will now assume now that since all these things are working, that means n equals to k will also be true. It's true. That's how simple mathematical induction is. It's just all about this. Now, after we then did this, we will then go on. Since we have now concluded that n equals to k is true. Now, if n equals to k is true, what is the implication on my equation, my expression? Look at what the implication is. Because don't forget now, we have done for when it was 1, we did it, you saw it. We have done for when it was 2. Now we are talking about when it's k. So that means we are saying that if n equals to k is true, that means we are saying when we kept on adding 7 plus 3 plus 7 plus 11 plus and on plus when we added for when it was k plus 4 k minus 1, we are now sure, because of the first 3 we have done, that if we added all these things, we added the first one, the second one, the third one, up till the kth one, where the n was k, we are now sure that it's going to be equals to k into bracket 2k plus 1. We are don't forget, we were doing, when we did one for the third one now, we said it was 21, and it was correct, it was good. So we can now conclude now that if we added up till the kth one, this is going to be the sum, what the sum will be. This is what the sum will be. That's an assumption. So this is our assumption. It's an assumption. Good. So it's like we have worked up till 1, 2, 3, up till k. We will then go on to now conclude that if we have assumed for 1 to k, let's now finalize our proof and say that, let's now try something. Let's now say, okay, the one after k, that's why we are saying k plus 1, that the one after k is also going to be true. That's the whole point, that the one after k will be true. So that's when we will now go on to now prove that that one after k will be true. So we'll now go on to prove that when n was equals to k plus 1 is true. It was true. That's the main work. That's the main work. That it's true. So the next thing you now go on to do is to try and prove this. Of course, even if you are trying to prove for n equals to k plus 1, you still use the same. This was the initial expression in blue, don't forget. This was the assumption in black. So then go on. We then go on to prove for n equals to k plus 1. What do we do then? We have 3 plus 7 plus 11 plus dot 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 plus 4. Don't forget is n equals to k plus 1. K plus 1 minus 1. We're now saying this should be, sorry, I should have written for k first. Don't forget, k plus 1 is after k. K plus 1 is after k. So we'll first have, before we add k plus 1, we'll first have for k minus 1. Then we'll now have plus. This is for when, this was when it got to k plus k here. But we are doing, don't forget, a step after k plus 1. So you'll be adding 4k plus 1. Don't forget, use your bracket to minus 1. Now we're now saying if we added all these things, that means we added up till when it was k plus 1. This is what we must get. If you have been saying this thing has been true all along, then when we added all these things, we are supposed to get k plus 1, 2k plus 1 plus 1. That's the whole concept. Now we are saying if you said that you have tried for the base step when it was 1, when it was 2, when it was 3, you are now assuming that when it was k is true. Let's say, okay, it was when it was k is true. Then that means when you went the next step after k, that means one step after k, is also going to be true. And for that being true, the mathematical expression for that is what I just wrote. That means you are saying you were adding first one, second one, third one, you added to the kth one, then you added the k plus 1, then you are saying the answer should give you what this expression said. This expression is what told you is the expression for the sum. So it's supposed, you are saying if this was the case, then it's going to be n is now k plus 1. That's k plus 1, 2 into bracket, k plus 1, then plus 1. Please, can you guys indicate if you are following me? If you are truly following. Now, the next thing to do now is that we want to prove that this left-hand side is equal to this right-hand side. That this left-hand side, that's what we want to prove. That left-hand side is equals to right-hand side. So what do we do? Left-hand side being equals to right-hand side. This is the concept around it. You will now go on. You know, all this one comes with you being smart as a mathematician. You want to now go on to say, this particular, look at this place. You can see that this place looks like something like what you have seen before. You can see it. These two things I marked in red, they look like each other. And this one here, this particular one here, it had an expression. So what you can go on to do now is to fix this expression inside this particular place now, because we want to prove that this whole left-hand side is equal to this whole right-hand side. And the best way to do that is to, if you can fix a more perfect expression here, since you don't know too many things there, you can fix that one here, add it with this, and check it out if plus adding it with this to give you this right-hand side. If it does, then that means you have been able to confirm that it's true. So see what we do next. We then go on to fixing this value there. We're fixing k into 2k plus 1. Now, this all displaced in red now. It has turned to this. Then I'm going to say plus this one now, plus 4 into k plus 1 minus 1. Now, this is left-hand side. Everything must be equal to what you have here. Everything must be equal to this right-hand side. So this is where we then need to go and solve mathematically. Now let's try and see if everything on the left hand side will be equals to the right hand side. So we try and solve this, and we see what we get out of that. So I want you guys to, while you're watching, I want you guys to, on your pen now, you try to solve, and let's see what happens. So what the best way to solve these things is that, in this case now, is that you will pieces everything. That means you will make everything bare. So you open up everything. In this case now, you'll be having k squared, 2k squared. You'll be having 2k squared plus k plus 4k plus 4 minus 1. Let me open the right hand side also. Opening this right hand side, let me start from saying k plus 1. This will be 2k plus 1 plus 2, then plus 1. If the students are not aware about the classes, then we should blame the reps for that. The reps are not doing their job perfectly in that sense, in making sure that the students are aware of the class. All right. Now look at this. This is the left hand side now. 2k squared. This is plus 5k. This is plus 3 equals to, this will be k times 2k. That will be 2k squared plus 2k plus k plus 2k plus 2 plus 1. This left hand side, I'm done with this left hand side. Let me see what happens here. Plus this will be 3k plus this will be 5k plus 3. Do you see what happens? Left hand side is equals to right hand side. So that means we have successfully proved that all the pins on that left hand side, those additions, was actually equals to the sum eventually. So once you say this, that means you have perfected your proof. And that's all. So you just conclude that by mathematical induction, you've been able to prove that this particular argument, this particular mathematical expression is true. And that's all. So I want to go into rules for divisibility under mathematical induction, because those are also places where you can be tasked with finding solutions. So if we still have time after, then we'll come back to some more questions on this type. But let's try and explain rules for divisibility. How do you solve questions on that? So this is the general concept of mathematical induction. Don't forget, as I explained, the first one is the base step. Understand this thing like as if you are trying to walk through a particular step or something, or you are trying to walk on a wood. Let's say these were woods, something like that, and you were walking. As I said when we started, for those of you that were not here, this is you here. They told you that this thing, that the woods that are here, that the woods that maybe the carpenter did, they told you that those woods are so perfect that you can walk on them, that it works well. Now, you put your step on this first wood. You saw that this works. You saw it did not break under you, did not collapse under you. Okay, you left that one, you put it on the next step. The first step we're talking about here is what is n equals to 1. You tried that one. You saw that what they said was true. You went on, you tried for n equals to 2. You saw that it was true also. You put your leg here also, n equals to 3. You saw that it works also. Then you don't want to keep walking, n equals to 4, n equals to 5, n equals to 6, and n equals to 10, n equals to 20. So you just go on to assume that, okay, with the work I have taken now, I can assume that if I got to n equals to k, that means it was 1 year, it was 2 years, if n was k, it's going to be true also. And that's what brings us to the second step, which is your hypothesis step. In this case, now in this hypothesis step, you don't necessarily put your feet on it, like walk on it. what you will just do is to assume. You can see that's why I left the gap here. So you will just assume that I'm sure that when I get here, when n was k, I'm sure that when I took the kth step, it's going to still be correct. That's the second step. Then, after you have assumed that, to put the final nail on this, to put the final conclusion, to be very sure that what this particular carpentry work, so to say, is true, you then assume that, okay, after that kth term, are you sure it will still work after that? That's what we then call like the inductive step. This is the case where you will go on to then prove that the step after n equals to k, which is n equals to k plus 1, is actually true also. It's that simple. It's that simple. So you don't need to ever be feel mathematical induction has any complexity. It's very simple. So let's solve rule for divisibility and let's see how we apply mathematical induction to rules for divisibility. Let's see. Let's see how we are able to apply this to it. So rules for divisibility. Okay, somebody is asking now, what if L left hand side is not equal to right hand side? Then that means you will say that the proof, the expression is not true. The expression is not, once it's not equal to right hand side, then that means what you have said is not true. So the main point is for you to prove that, although if they told you to prove by mathematical induction that this is the case, that means it was actually the case. But imagine they just told you to test if it was true or not. In that case, they're more like assuming it's either true or it's not true. They're not telling you whatever is happening. But if they told you that prove by mathematical induction that this is the case, you must find a way to make sure that left hand side is equal to right hand side, because that means they are sure that was the case. The only point was that they wanted you to just show to them that was the case. But if they say you test if this particular expression is true, then what you need to go on then to do is to check if LHS left hand side was equal to right hand side. And if it wasn't, then you tell them that this particular expression is not true. So let's talk about divisibility. Let's talk about rules, or do we call it rules for divisibility or something? Under mathematical induction. See, the same steps we have been following, the same steps that has to do with base step, inductive hypothesis, and then proving, is the same step we're going to follow in this particular case also. So what do we do? Let's take 2 questions on rules of divisibility, simple ones, so that you can start from that place. Look at this particular thing, n cubed plus 2n. You have n cubed plus 2n. They now say prove that this n cubed plus 2n is divisible by 3. They say you should prove that this particular expression is divisible by 3. So how do you prove that this is divisible by 3? How do we prove that the expression of n cubed plus 2n is actually divisible by 3? The same steps I told you. The first step is to go on to prove the base steps. So go on to assume when n was 1, you said the meaning of this is that n cubed plus 2n, that means n taking integer values. So let's try if n being 1 was actually divisible by 3, the base step. Then we can go on to try for when n was equals to 2. Then we can then go on to try for when n was equals to 3. We can stop there. We don't need to keep doing for till 10, till 11, till 12. When we stop at around maybe that n equals to 3, or even n equals to 2, we can then go on to then assume that n equals to k was also the case. So let's see for n equals to 1. If n was equals to 1, that means 1 cubed plus 2, 1. What did he give me? He gave me 1 plus 2. That is 3. Now, you can see that This is 3 times 1, which shows that it was divisible by 3. Because 3, it will be divisible by 3 in one time. That means 3 can go in 3 one time. 3 times 1 is 3. That's nice. You see, this works very fine. Let's see for when n was 2. That will be 2 cubed plus 2 times 2. That will be 8 plus 4. That's what? 12. You can see this is 3 times 4. That means 3 can go in 12. It's divisible by 12 4 times. It works. You see, our inductive step is actually making sense. Our inductive step is actually making so much sense. So let's go on to check for 3 cubed. That means for when n was equals to 3, that will be 2 into bracket 3. That will be 3 raised to the power 3 is what? 27. 27 plus 6, that's what? That's 33. This obviously is 3 times 11. That means it's divisible by 3 11 times. Now we can see that our base steps all works. More like, imagine, as I said already, you were taking those steps. You have stepped on the first one, you have stepped on the second one, stepped on the third one. Then you can go on to assume that if I keep on stepping, if I go to n equals to k, it's going to be true. So you go on to assume that n equals to k is going to be true. This is your inductive hypothesis. Now, in this case, you then, after assuming n equals to k is true, what's the expression that will actually happen? What will happen will be k cubed plus 2 into bracket k. And whatever answer you got must be 3 times a particular integer. Maybe we'll call it m. Whatever answer we got will be that. Because if n being k is divisible by, if n being k is divisible by 3, the answer you must get must be 3 times something. So we don't know whatever that is because we don't know what k, we don't have a number for k. So we just put m there representing whatever it may be. Maybe 100, maybe 103, maybe 205. It could be anything. We just know that when n equals to k happened, it was 3 times something. That means it was divisible by 3. That's certain. That's clear. Good. Now let's now move on to now prove the final step. So you have worked on when n was 1, it worked. When n was 2, it worked. When n was 3, it worked. You then went on to assume that when n was k, it's going to work. Then your final proof is, a step after when n was k, is it going to be true or not? You now need to go on to prove that. That's the whole idea to this. So you need to go on to now prove that n equals to k plus 1. You need to go on to prove that n equals to k plus 1 is true also. How do you do this? Very simple. Look at this. We have, if n was equals to k plus 1, that means this expression will turn to k plus 1 cube plus 2 into k plus 1. That's what it is. And if, let me just say this on the side note, if it was actually true, you must get an answer that will be 3 times something. You must get that answer. So let's see what this will give us. It must be 3 times something, or something that shows that it's 3 times something. So that's the point. So this is when n was k plus 1. Now, don't forget, we're proving that n cubed plus 2n is divisible by 3. So what do? Let's try and open our, this is n plus 3. Let's try and open this. Can you go on to open n plus 1 cube? Go on to open n plus 1 cube. N plus 1 cube, what do you think is going to give you? Of course, that will be k plus 1 cube. That will be k plus 1 into k plus 1 square. What's k plus 1 square? K plus 1 square is k cube, k square plus 2k plus 1. So multiply all this by k plus 1. This will be k cube plus 2 k square plus k square plus 2k plus 1. So this will be equals to what? This will be k cube plus 2k square, or plus 3k square rather, because this is 2k square plus k square, then plus 2k plus k, that's plus 3k, then plus what? Plus 1. That's the expression for k plus 1 cube. Then this will be plus what? Plus 2k plus 1. I'm sure I've not cheated at all. I'm sure everybody can relate to what I'm saying here. I've not cheated at all. This works well. All right. Now, this is the place where I expect full attention, because you need to understand how this thing. Don't forget, we are trying to prove that this is divisible by 3. So you need at this point to be very smart mathematically. You need to be very insightful. You should be able to see things much clearer. Look at something here. I'm sure you understand that when you always got to this, your n equals to k plus 1, in almost every cases, you always use for when your n was k. Just in case you have forgotten, this was the place where your n was k. This was when n was k. This is the expression here, which I said was supposed to give you a value that was 3 times m, 3 times a particular integer m. So if this is the case, now look at something. Can you see something happening here? Can you see any expression that has to do with this n equals to k? Can you see any of it in this particular place? Look at it. For n equals to k, we had k cube plus 2k. Can you not see k cube here plus 2k happening here? So if I decide to put that close to each other, I have k cube plus 2k. Of course, I already know that k cube, this particular expression here now, will be a multiple of 3, because it already told me that k cube plus 2k was divisible by 3. So I know this one already. This particular k cube plus 2k will be divisible by 3. So I've settled that one. That one is settled. So let me go on to fish out the other places. I have plus 3k squared. Then I have plus 3k. Are you sure I did not make a mistake somewhere? I think. Okay, it is 2k plus 2. Thank you, sir. Thank you to that person. 2 times k, 2k, 2 times 1, 2. Thank you. So this is 1 plus 2. That will be 3. So at this point now, I can already see from this my inductive hypothesis, that's this step 2, that my k cube plus 2k was equals to 3m. And 3m indicates that that was divisible by 3. So that means without further ado, I know that this place is divisible by 3. So I can write it. Don't mind me if I write it now, that this place is 3m. Don't mind that m there. Please understand that that m signifies any integer. The major thing here is not the integer, is that the integer was multiplied by 3, which is what has been established already. Since the integer was multiplied by 3, once any integer that multiplies 3 will always be divisible by 3. So simple. Any integer, 3 times 1 million, 3 times 101 will be divisible by 3. Because once you say divided by 3, 3 records 3. So the leftover, if you say 3 times 1001 divided by 3, the answer will be 101 times. It's so simple. So once you have 3 times a particular integer, that value will always be divisible by 3. So this means that in this case, this 3 times m is actually divisible by 3. So we have established that this side is divisible by 3. Let's go and see if we can establish this side also. That's the whole idea of this thing. It's for you to just be very much open-minded. Now look at this. This one is 3m already. Let me write plus. If I factorize 3 outside here, which I love to do, because don't forget, my whole idea is to find a way to prove that this thing is divisible by 3. So the fact that I'm saying 3 here works well. I love it. I love that I'm saying 3 there. So I go on to bring out k cube plus k plus 1. Now, this one is divisible by 3 already. Can you tell me, do you think this expression will be divisible by 3, this particular one? This one, this 3 into brackets, and k cube plus k plus 1. Will it be divisible by 3? The answer is absolutely yes. You know why? Don't forget, k is an integer because we're moving. We said n was 1, n was 2, n was 3. So obviously k was an integer. So let's say k was like, I don't know, 152 for instance. Whatever you do with 152, if you cube 152 and add it plus 150, of course, let's say k was 152. 152 cube plus 152 plus 1 will give you an whole number integer also. And don't forget, I already told you that 3 times any number, if eventually the number was 1,010,000, if it was 3,005, if it was 500,200, whatever value this thing gives you, as long as it is multiplied by 3, that number will be divisible by 3. So the fact that I'm able to do this already tells me that this particular thing, because this is like almost like I'm having now, it's like I'm having 3m plus 3p. Let's assume this value here, with assumption that this value here is a p is any integer. Let's call the integer p. So 3 times any integer plus 3 times any integer, another integer. Let me now ask the class, do you think this will be divisible by 3 or not? Do you think 3 times a particular integer, let's use a simple one, 3 times 4 plus 3 times 11, do you think this value will be divisible by 3? Go on and investigate. Try it for any value. Try it for any value. Oh, you guys are spotting my listening. It's actually k squared. Thank you. K squared, yeah. All right. Thank you very much. Thank you very much. But actually, if it was k cube, if it was k squared, whatever it was, but it's true that it's actually k squared. Whatever it was, k squared or k cube, whatever, as long as the k is an integer, whatever you do to it plus the integer plus 1 will give you a number that will be divisible by 3. Now, if you investigate this, one thing you will always get is that this number will be divisible by 3. But you can even go on to factorize this and say this is equals to 3 into m plus p. This makes it all nicer. It makes it all much more beautiful in the sense that when you say a particular integer plus another particular integer, 100 plus 201, whatever the answer is, as long as it's a whole number, an integer value, when you multiply that with 3, it will always give you a number that will be divisible by 3. So without any fear of contradiction, I can clearly say that this particular expression, n cubed plus 2n, is divisible by 3. That's the level of confidence I want you to have when you are sitting in front of any question that has to do with mathematical induction. Just move on step by step. You can never go wrong. Now, I want you guys to, while we are still together, to try this question. Try for n squared. I want you to try for n squared plus n. Is it divisible? N squared plus n, not 2n. Is it divisible by 2? Just those of you that have been following me, just try it. Try it on your own now. Try it on your own. Follow the same step. Just try it. Try it. Just get your hands dirty and see how this works. Follow the steps. Follow the steps. Your base step, your inductive hypothesis, and then go on to prove that n equals to k plus 1 is true. You will never go wrong. So try that very quickly. Try that very quickly. Let's see how it goes. If you have not given a thumbs up to this live feed, please do that very quickly. So this is how we do mathematical induction. It's quite so simple. Actually, very simple. So you just need to follow the steps and learn how to move through the procedure. Has anybody been able to prove this? Okay, let's do it together. While you're proving, just check out what we're doing, and you will confirm if your answers are good. All right, we start again with the base step, and we have to move confidently. All right. So what's the base step here? N equals to 1. Let's try for n equals to 1. When n was equals to 1, we put in 1 here. We have 1 squared plus 1. We got an answer of 2, which is equals to like 2 times 1 here. We saw that this was divisible by 2. Of course, it goes 1 time. Nice. We go on to do 2 squared plus 2. We got 4 plus 2. That's 6. That was 2 times 3. It was also divisible by 2. Nice one. We then go on to do 3 squared plus 3. 3 squared is 9 plus 3. That's what? 12. We saw this was 2 times 6. It was divisible by 2 rather. So looking at this, I've been able to climb that very first 3 step. 1, 2, 3. It doesn't have to be 3 all the time, by the way. You can just, it's possible you just jump on 1. Sometimes you may just jump on 1 alone. So yes, exactly. I'm actually trying to respond to that. It's not compulsory you have to do 1 to 3. I'm doing this 1 to 3 just for the sake of making sure we can make a very good analogy. So you can actually just stop on the first 2. Sometimes even some people may stop on first 1. So that's not compulsory. So when you are done proving this base step, then you go on to your assumption. So we now assume that n equals to k is true. And if that was the case, that means we'll be having k squared plus k being true. And that will mean our answer will be something like 2 times n. Don't forget, whenever it was true for 1, we said it was 2 times 1. It was true for 2, it was 2 times 3. When it was 3, it was 2 times 6. So if it's true for k to be 2 times something, let's just assume that thing to be, n. So we then need to go on to now prove our inductive step. Prove that it is true when n is equals to k plus 1. So we need to prove that this is true. So how do we prove that it's true? Let's go on to fix for when it was k plus 1. That means we have k plus 1 squared plus k plus 1. Of course, that's putting n as k plus 1 into this particular expression, the original expression. Opening this up, we would have k squared plus 2k plus 1 plus k plus 1. This will give me, now look at it. I can already see what's happening here. In my inductive hypothesis, when I fixed in n as k, I saw that k squared plus k was 2m. So I want to quickly isolate k squared plus k. Yeah. So that I want to make work easier for myself. Don't want to go and be passing through too many long chords. So now look at it. K squared plus k. This was the inductive hypothesis step. I know this one already by default from what I have here is 2m, which was divisible by 2. So let me go on to try to work with the rest. So I'm left with 2k plus 2 because 1 plus 1 is 2. So I'm left with plus 2k plus 2, which obviously, if I decide to factorize this out, I'll factorize 2 into brackets k plus 1. All right. I'm sure everybody can follow on that. So this will be 2m plus 2 times. Can you tell me k plus 1? Will k plus 1 be true or not? Will be an integer value? Will this k plus 1 be an integer value or not? Of course, it will. If you have any integer value, let's say you have an entire value of, let's say, 11. 11 plus 1 will still be an integer. 20 plus 1 will still be an integer. So k plus 1 will always be an integer as long as k was an integer. So notice this is an integer. Let's call the integer a value of, let's say, p. So we can go on to say this was equals to 2 into bracket m plus p. Don't forget, m was an integer, p is an integer. Adding two integer values will give you what? An integer. So this will be 2 times a particular integer. Who knows, if we want to make things more delicious, we can go on to say this is equals to 2 times y. We say y is equals to m plus p, and y is also an integer. Just to make things more nicer. Just to make things more nicer. Sorry for that. That was like a glitch. Just to make things more nicer, that's why we have okay, so what is which last part do you have issues with? This thing I put here, or this particular thing I put here, this y I put here is, you don't get confused though. How do I get this part? This is the whole thing now. This is the whole thing when we extracted this. So this was the whole thing. So you know already that k squared plus k was 2m. So I isolated it, and I'm left with 2k plus 1 plus 1, which is 2k plus 2. So this one I'm doing here, don't get too confused. So this y here, you can leave it. It's just to say an integer value m plus another integer value m will always give you an integer value y, or whatever we want to call it. So are you still having issues? Is that person still having issues? Are you still having issues? Okay, now you know what we're going to do? We have take this question down. This one is just like a very few steps. I don't expect you to waste time on it. And let me see what you do with it. I want to rub this initial step in case somebody is still trying to flow with the first one. Okay, nobody's having issues again, so this is nice. So I expect you to ace your exam there. So prove by mathematical induction that this is the case. Prove by mathematical induction. Okay, thank you. You have gotten it. Okay, that's nice to hear. So prove that this is the case. Can you prove that quickly and just indicate if you... I'm sure nobody is having issues there. Prove very quickly. Prove under like 2 minutes. I want to see your confidence now, so I would love to see you make advancement before I do mine, so that you just follow the same step. This case now, you are trying to prove that this particular thing, that means you summing all these things up. They said this was the sum, this is the formula, this is the function that works for the sum of all these values. Of course, when you put n as integer values, you put n as 1, put n as 2, and so on. So they said this was the case. So prove to them that this is the case or not. Of course, you start with your inductive step. Sorry, you start with your base step. Can we do that under 1 minute? At this point, I want you to move with confidence. That's like a very key thing. Move with confidence. Like, move on without making any mistakes. So let me start mine. The base step for n equals to 1. I know that this is the first sum. So my n equals to 1. My sum of 1 was 1. So I go on to investigate if that was the case with the formula. From the formula, they told me that if it was, the sum was always going to be 2 raised to power n minus 1. That's 2 raised to power 1 minus 1. That was equals to 2 minus 1, which is equals to 1. So I saw that they were equal. They worked well. I checked for n equals to 2, which I'm going to stop at n equals to 2. That would be 1 plus 2. The first two, the sum of the first two, that was equals to 3. The sum of the first two is equals to 3. That means we have what? The next one for the sum, we have 2 raised to power 2 minus 1. So we have 4 minus 1, which is equals to 3. You see, this works also. So our base steps has worked very fine. But what matters now is to going on to assume, before you then go on to prove that n equals to k is true. If you prove that this is true, what are you going to have? Of course, you're going to have 1 plus 2 plus 2 raised to power 2 plus 2 raised to power k minus 1 being true. And if this is true, it will be equal to 2 raised to power k minus 1. So you then go on to prove that n equals to k plus 1 is true. How do you prove that? That will be 1 plus 2 squared plus dot 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 plus, before you go to k plus 1, you go to k first. K minus 1, then you then go to k plus 1. 2 into k plus 1 minus 1. This must be equals to 2 raised to power k plus 1 minus 1. I'm sure you guys are following. I'm sure you can flow with what we're doing. So I can see this already exists here. All this exists already. Yeah, this is it here. So I can just write this as 2 raised to power k minus 1 plus 2 raised to power k plus 1, which is k plus 1 minus 1. That's k. So this is 2 raised to power k plus 1. Of course, you understand that that's k plus 1 minus 1, which is k plus 0, which is k. So this must, if this is the case, 2 raised to power k minus 1 plus 2 raised to power k must be equals to 2 raised to power k plus 1 minus 1. So this is what we have to prove. This is the proof we have to work with. And let's see what we can do. Now we want to prove that. So I go on to group this together. This is 2 raised to power k. 2 raised to power k plus 2 raised to power k will be 2 of 2 raised to power k minus 1. And this is equals to 2 raised to power, this is 2 times 2 raised to power k minus 1. I'm interpreting this as 2 raised to power k times 2 raised to power 1. So in this case now, you can see that this will be equals to 2 raised to power 1 plus k. Oh, sorry, 2 raised to power 1. But let me just leave it that way. I don't need one. I did not need to have converted it. 2 raised to power k plus 1. Let me just leave it that way. So let me work on this side. So what I have here is 2 raised to power 1 plus k, which is the same thing as 2 raised to power k plus 1 minus 1, which is still the same thing as, you see, left-hand side now is already equals to the right-hand side. So proved. Once you're done with this, you're good to go. So once you're done with this, that's all. So this is how you work with mathematical induction. Very simple, very straightforward. It's not complex at all. So how do you guys feel? Let me get your feedbacks before we end this class. We have more topics to deal with tomorrow. From tomorrow, we'll be going home with our regular solving of lots of questions, and I really hope we can what are you getting wrong? Tell me what you're getting wrong, please. Can you, those of you talking, can you please, what don't you understand? This is your assignment, please. This is your assignment. Can you prove that this is true? So, what are you getting wrong? Those of you that had those conversations with, what are you getting wrong? This last side, when we got here, of course, we had 2 raised to power. This was what we had. Before we got here, we had something like this. 2 raised to power k minus 1 plus 2 raised to power k. This same thing was the same thing here. So this same thing was the same thing here. Now, when we had this, well, 2 raised to power k, 2 raised to power, it's also more like when you had x. If you had x plus x, you would say the answer was 2x. So when we had 2 raised to power, can you hear me now? Okay, so what I was trying to say is the person that was asking me about this particular thing, I said this was the same expression we had here. This same expression we had it here. So 2 raised to power k plus 2 raised to power k is obviously 2 of 2 raised to power k, just like how you had x plus x being 2x. If I say what's x plus x, you say it's 2x. If I say what's y plus y, you would say it's 2y. So when you have 2 of 2 raised to power k plus 2 raised to power k, you'll be having 2 of that minus 1, obviously. This is the minus 1 here. So 2 raised to power 1 is actually 2. 2 raised to power 1 is the same thing as 2. So it's more like, okay, let me do something here. Imagine what I had there was 2 raised to power 1 times 2 raised to power k. So the law of Benesis told me that this is the same thing as writing 2 raised to, you will have, if you have the same base, then you can add their power. That will be 2 raised to power 1 plus k. That's what you had here. Is it making sense for that person that had the complaint? So that's what you have. So having that now, you can obviously change, instead of 1 plus k, you can change it to k plus 1. That will be k plus 1, and then 2 raised to power k plus 1 minus 1. Now, the right hand side here is the same thing as the right hand side here. So once the left hand side is equal to the right hand side, then we have successfully proved our expression. So this is the assignment I would love you to make do of and try to prove this. You can do this during you can do this at the end of the class so that you get very. Am I still mute? Or you can't hear me again? Are you sure you can't hear me? Who can hear me right there? Please, can you indicate if you can hear me? Can anyone hear me there? Okay, so if you can hear me, that's nice. So, all right. So please make do of this particular question. You can do it right now after this live feed, so that you can be able to consolidate your knowledge on mathematical induction. So I really hope from now we can go on to tackling lots and lots of questions so that you can get very, very strong in this aspect, because it's a particular aspect that is very examinable because it proves the smartness of students. Actually, it's quite very simple. Understand the analogy I gave you. I gave you an analogy of, look at it as you are climbing a step. So you want to always move step by step. So when you move that way, you don't go wrong. So that's why I'm telling you, the next thing we have to do now is to solve lots of questions. So anything you can do now, go and look for so many questions. We'll be solving some of them in our classes. We'll be starting the classes for this weekend tomorrow. So make sure you're prepared. Make sure you're very much prepared. 1 hour, and you're going to solve several questions on several topics. So guys, this is where we're going to stop for this night. Make sure you inform everyone. We have lots of work to do. All right, guys, it's been a lovely moment. At this point, I'll be wishing you all the best for the night.